In this video, we're going to be talking about topics from chapter 5.2, the natural logarithmic function, specifically integration. This is our first video in our Calculus 2 topics, and there's going to be some refresher videos in the beginning here to talk about some of the things that we also talked about at the end of Calculus 1. Just going to pick up there in case someone's Calculus 1 course didn't end at the same place as the Calculus 1 topics that we talked about before, and they cover these topics in Calculus 2, because there's some overlap there in the end of Calculus 1 and the beginning of Calculus 2 in a lot of schools. So that in mind, I also want to say that we're probably not going to have a video like this with notes for every single Calculus 2 topic. There will be several of them that I'll just do some example problems without the full notes that include the theorems and things of that sort. So there will also be plenty of supplemental examples to come later for Calculus 2. I look forward to working through those with you. All of this content and those supplemental examples will be based off of the Larson-Edwards calculus textbook. All right, so let's go ahead here and recall that the differentiation rule for natural logs is d dx of ln of the absolute value of x is equal to 1 over x. Reason we use the absolute value there is so that we get the domain to be the same on the left and the right. On the right-hand side, x can be anything other than 0. Since we can't stick negatives inside of logs, we use the absolute value bars to force that to be positive. And then those two expressions have the same domain on the left and the right. We don't need to restrict the domain of 1 over x that way. So when we are going to integrate, that's why that's going to force the absolute value bars on the right-hand side here in number 1 for theorem 5.5 that says that the log rule for integration, if we let u be a differentiable function of x, for the general rule over here, we'll get to that, but for the basic rule, 1 over x dx, the integral of it is going to integrate to be ln of the absolute value of x plus c, and that keeps our domain on both sides. X cannot be equal to 0. All right, also the derivative of ln of the absolute value of u will then be 1 over u times du dx because of the chain rule over here. So then it's going to follow, because of that, if we take the antiderivative of both sides here, that the integral of 1 over u du is going to be equal to ln of the absolute value of u plus c. So we just talked about this, the log rule for integration, and we'll use that to integrate rational functions. Remember, a rational function is in the form of p of x divided by q of x, where q of x is not equal to 0. You might also say something like n for numerator and d for denominator, but let my tablet catch up here. So we're also going to integrate some trigonometric functions here in just a second. X over q of x. This is rational function like that. Remember, q of x can't be equal to 0. All right, so let's go ahead here and let's do this integration. Let's pull the constant multiplier of 2 out front, and then we have the basic form 1 over x dx. So we're going to have 2 times ln of the absolute value of x plus c, like that. Then if we perform some definite integration here with limits of integration, we're going to let u be equal to our denominator. Du is going to be the derivative of the right-hand side with a dx on the end of it. So I need a 2x dx. I'm going to fix this by multiplying by 2 on the top and 1/2 on the outside. go back and watch our last video in Calculus 1 on u substitution if you want to see what I did there. You also could have solved for dx there, and you would have gotten 1/2 of u, and you could have stuck that in there and then pulled the 1/2 out. I'm not going to go through all the steps from the last video in Calculus 1 where we change our limits of integration and all that. I know now that the form tells me that this is 1/2 ln of the absolute value of my u. And I'm just going to stick my limits of integration there and avoid my plus c because this is not indefinite integration, it's definite integration. That tells me this is 1/2 ln of 3 squared plus 1 minus 1/2 ln of the absolute value of 0 squared plus 1. That's 1/2 ln of, don't need the absolute value bars here because this is going to be positive. 9 plus 1 is 10, minus 1/2 ln of, again, this is going to be positive. 0 plus 1 is 1. ln of 1 is 0, so all that's a big fat 0. And we get 1/2 ln of 10 is the correct answer. Your textbook is going to break down answers for composite numbers like that, like so, as prime factors, and then use your log properties like so. That's the same answer. And if you stick that in your calculator to get an approximate answer, you would get something along the lines of that. Now, in example 3 here, if we let u be equal to x squared plus 2x, our du is going to be 2x plus 2. And we're going to want to multiply here. This is 2 times x plus 1, so we want to multiply by 2. And we have a 1/2 on the outside then. So this is going to be 1/2 ln of the absolute value of x squared plus 2x, like that, plus c, since this was an indefinite integral. And we're going to maybe want to split this up since there's x's in both of them, that's x times x plus 2. So this is 1/2 ln of the absolute value of x plus 1/2 ln of the absolute value of x plus 2 plus c, something like that. All right. Let's go ahead now and look at this improper integral. It's improper here because the degree of the top is well, it's an improper fraction that I'm integrating. Let me not call it an improper integral. That'll be something else that we do in chapter 8. So this integral of this improper fraction where the degree of the top is greater than or equal to the degree of the bottom, we're going to use long division here. So we want x squared plus 1 into x squared plus x plus 1. So x squared goes into x squared 1 time, squared and 1, change my signs and add. Now it's proper that x has a lower degree than x squared plus 1. So that becomes the integral of 1 dx plus the integral of x over x squared plus 1 dx. Going to fix my du there, where u is equal to x squared plus 1. du is 2x dx. Come on back to my regular color here. The integral of 1 dx is going to be x, plus we have that 1/2 ln of the absolute value of x squared plus 1 plus c. All right, now we get to do some fun integrals with trig. We're still looking at the top being the derivative of the bottom. So the bottom is tangent. The derivative of tangent is secant squared. So this is a du over u situation. So we're still going to get ln of the absolute value of u plus c. So because u is tangent x, we get ln of the absolute value of tangent x plus C. Now let's look at this next one. While the degree of the top is 1 less than the degree of the bottom, I actually want to see an x squared in the bottom to help me get this du. So I'm going to multiply out my u there. It's x plus 1 times x plus 1, which is going to give me x squared plus 2x plus 1 for my u. So my du is going to be 2x plus 2. Well, I don't see my plus 2, so I'm going to have to add and subtract it. So I have 2x plus 2 over x plus 1 squared dx, and then minus 2 over x plus 1 squared dx, like that. Okay, so now I have du over u. Let's call this x squared plus 2x plus 1 here. So this is a du over u situation here. Added and subtracted 2. I kept my denominator the same. Those are just the different forms of that same denominator of u. Now I'm going to choose a different u for the one on the right because I want u to be x plus 1 and du to be equal to dx. So I can pull that -2 out front and write this as u to the -2 du. So this is ln of absolute value of u. Let's call this v, just to choose the next letter in the alphabet so I don't get them mixed up. We'll be dealing with some v's later on, but that way you know that this u over here and that u and that over there are going to be different. Sometimes we'll use t's as our additional variable for substitution. And so this is going to be minus 2v to the -1st over -1 plus c. So ln of the absolute value of u was x plus 1 quantity squared, like that. And that'll be important. I'll use a log property in just a second. Minus a negative is going to be a positive. 2 over v is x plus 1 plus c. I'm going to use my log properties to bring this down here and make this 2 ln of the absolute value of x plus 1 plus 2 over x plus 1 plus c. This is always positive if it's squared, so I'm going to keep those absolute value bars to make sure that this is always positive here. All right. Sometimes simplification with trig identities may be required. The most important thing when evaluating integrals is to just dive in and try something. Even if your method isn't correct, you learn something with each attempt. We said the same thing about limits, and that's a copy paste. I needed to change the word limits to integrals there. So let's evaluate tangent x, and let's do that using a quotient identity from pre-calculus. The tangent is sine over cosine. And then we can make our denominator u. So that makes our du equal to a negative sine x dx. So we need to have a negative and a negative there. So that's going to give me a negative ln of the absolute value of cosine plus c. And we like for tangent to be related to secants usually in most textbooks. So I'm going to take this -1 that's right here back up as an exponent on that cosine to tell me to find the reciprocal of it. And I'm going to write this ln as the absolute value of secant x plus c. This is actually okay to say that it's negative ln of cosine of x. If you do that, then you're not going to have a negative in your cotangent formula, and that's kind of weird. We usually have the negatives in our cotangent formulas, and we don't have the negatives in our ones that aren't cofunctions. So this just helps us to be consistent so that when we get to cotangent of x dx, that it's going to be negative ln of this cofunction plus c when we get there. Okay, does that make sense? It's just for the purposes of being consistent with our notation, help us to memorize those formulas that tangent is related to secant, cotangent is related to cosecant, and because cotangent is a cofunction, we're going to have a negative in that formula. But it's absolutely correct to just say negative ln absolute value of cosine plus c. That's the same thing as ln of absolute value of secant plus c. All right, the derivative of the secant integral, we're going to need to use a integration factor, this is called. More about this when you get to something like differential equations, but I'm going to tell you that we're going to multiply by a form of 1, secant x plus tangent x over secant x plus tangent x. If you want to see why we chose this, I can explain that to you later, but I'll say right now we chose it because it works. I know that's not a very satisfying answer, but we can go ahead and solve it some other ways and find out that this has to be the integration factor. For right now, though, we're going to use this technique and just have this given to us because someone found this already. I'm going to multiply the numerator and get secant squared x plus secant x tangent x over secant x plus tangent x. We're going to let our u be our denominator of secant x plus tangent x. We're going to let our du be the derivative of secant is going to be tangent squared x. Sorry, I did it again. The derivative of secant is secant x tangent x, and the derivative of tangent is secant squared x. See, I'm looking at this trying to make this show up, and it's backwards here. So that's my fault. So we have exactly du because the order of addition doesn't matter. That's du over u. So we get ln of absolute value of u plus c is ln of the absolute value of secant x plus tangent x plus c. So guidelines for integration when using u substitution and log integrals. Just know your basic list of integration formulas from chapter 4. That's actually where we're going to start in chapter 8. So 8.1 is just going to be a review of this. It's a good place to look in your textbook for everything. Find an integration formula that resembles all or part of the integrand, and by trial and error, find a choice for you that will make the integrand conform to the formula. The things we've been working on today, we wanted u to be the denominator, and we wanted the numerator to be the exact derivative of the denominator. When you cannot find a u substitution that works, try altering the integrand using trig identities, multiplication by 1, like we did here. That's with an integration factor. Add, subtract the same number, like we did here, where we added and subtracted 2. so on. Like that. We've shown all these different techniques so far, and using long division. Use long division when it's in proper fraction. Just try something and be creative. If you get really stuck and need a little push in the right direction, either look at your integration tables that are in the back of your book. Or computer algebra software that can find antiderivatives, go ahead and use it. If it's a definite integral, go ahead and do it as an indefinite integral just to see what type of function it shows up with. That'll give you some hint which direction you're supposed to go in, but don't just write down the answer and not figure out how to perform the steps, because on the test, you're going to have to show your steps for credit, and you're not going to be able to use that software to just do it for you. So practice your homework like you're going to need to show the work on the test. If you get stuck, it's okay. Most of the time, look at your syllabus and your college policies to make sure this is okay, but it's usually okay in this class to use some kind of computer software like Wolfram Alpha, Symbol Lab, Maple, Mathematica, something like that to actually help you. And a lot of colleges and universities might even have a dedicated computer lab that has this type of software on it. You may even be taking a lab along with your calculus class to teach you how to use Maple or Mathematica or something like that to help you be able to do these integration techniques. So go ahead, if you are learning those things, use that software, practice using it with these integrations and see how the computer does it. And you might actually think about doing it in a different way, and you might want to learn how to compare those answers and see how they're the same thing. All right, enough on that. Just know that there's multiple techniques, and the different techniques that you're going to use might give you different correct answers. Check your result by differentiation to obtain the original integral. So that's what I'm getting at. Even if you do it different ways and you get things that look different, if you take the derivative of both answers, you'll get back to the original. They'll really be equivalent answers that are only different by a constant of integration, even if they don't look like it. All right, that's it for this video, and we're going to come back next time and we'll talk about 5.5, where we'll talk about bases other than base E and how we deal with differentiation and integration of a to the x. See you for the next video.